You ever find yourself just staring at a complex machine, like a crane or an excavator, and wondering, how does it all work? How do all those gears and levers and pistons move together in what looks like perfect harmony? Well, today we're going to pull back that curtain. We're breaking down the fundamental rules that govern how pretty much everything moves in our world. Okay, let's just dive right in with this dump truck. I mean, look at it. You've got a ton of moving parts, right? The wheels are turning, that big hydraulic arm is extending, the bed is tilting. It seems incredibly complicated. But, and you gotta believe me on this, it's all governed by just a handful of basic principles, and we're gonna figure them out together.
But before we can really get our hands dirty analyzing a machine like that truck, we need to be on the same page. We need a shared vocabulary to describe what's actually happening. You can think of it like learning the basic grammar of movement itself.
And that language, it's called planar kinematics. Now, I know that sounds super technical, but don't worry about the name. It's really just a way of describing and predicting how things move in a flat, two-dimensional world, which it turns out covers a huge number of the machines we use every single day.
So, what does this formal definition actually mean in plain English? Well, rigid bodies just means we're talking about solid objects that don't bend or flex, okay? And planar means the object is basically moving flat, like a car on a road or a record on a turntable. So we're really just studying the official rule book for 2D motion. Simple as that.
Now, here's what's so cool about this. All of that seemingly complex motion we see out there, it can all be broken down into just 3 basic types. Seriously, that's it. Once you get these 3, you can pretty much understand any mechanical movement you see.
All right, first up, let's start with the simplest of the 3, pure translation. This is our foundation. This is the absolute baseline for understanding how things get from point A to point B.
So the whole idea here is that the object moves, but it does it without changing its orientation at all. Imagine you're carrying a full glass of water across a room. If you do it perfectly, the glass translates. It moves, for sure, but it doesn't tilt or spill. It stays perfectly level. And translation actually comes in 2 flavors. You've got rectilinear, which is exactly what it sounds like, moving in a perfectly straight line, kind of like an elevator going up and down. Then you've curvilinear, which is a bit more interesting. The object follows a curved path, but, and this is the critical part, it still doesn't actually turn or tilt. And a Ferris wheel is the absolute perfect example of this. Just look at one of the cabins. It's following this huge circular path, right? But the cabin itself doesn't flip upside down. It stays upright the entire time so you don't fall out. That cabin is doing curvilinear translation. It's moving along a curve, but its orientation never, ever changes. So here's the big takeaway for translation. For any kind of translation, it doesn't matter if it's straight or curved. Every single point on that object is moving in exactly the same way. Same direction, same speed, same acceleration. That's what makes it pure translation.
All right, so that's our first building block, moving without turning. But what about the opposite? What happens when an object turns without actually going anywhere? Well, that brings us to motion number 2, pure rotation.
Think about the hands on a clock or the gears in a machine like this one. They're all pinned at a central point, a fixed axis, and every other part of them just moves in a perfect circle around that center. This is rotation in its most pure, simple form.
Now, to describe all this spinning, we use a few new terms, but honestly, they just answer really simple questions. Angular position is just asking, hey, where is this thing pointing right now? Angular velocity is asking, okay, how fast is it spinning? And angular acceleration is just asking, is that spin getting faster or is it slowing down? That's all they are.
And here is the absolute key difference between rotation and translation. Think about a spinning record. A tiny speck of dust on the outer edge has to travel a much bigger circle in the same amount of time as a speck of dust near the center, right? That means it's moving way, way faster. All the points have the same angular speed. They're spinning together, but their actual linear speeds are totally different depending on how far they are from the middle. All right, so we've got moving without turning, that's translation, and we've got turning without moving, that's rotation. So, what do you think happens when we put them together? Well, let's find out, because this is the grand finale.
I mean, this is the big question, isn't it? Because when you look around in the real world, very few things only translate or only rotate. Most of the motion we see is a mix of the two.
And the answer is, you get what we call general plane motion. This is the one. This is the motion you see pretty much everywhere you look. It's just translation and rotation happening at the exact same time.
And a rolling wheel is the absolute classic example of this. Take a look at the axle right in the center of the wheel. It's just moving forward in a straight line. That's pure translation. But at the same time, the wheel itself is spinning around that center. That's pure rotation. General plane motion is just both of these happening at once. It's a combo move.
So let's do a quick recap of our 3 building blocks. We have translation, where the object moves but its orientation doesn't change, like that Ferris wheel gondola. We have rotation, where it spins in place around a fixed point, like the hands of a clock. And then we have general plane motion, which is just the combination of the two, like a rolling bicycle wheel.
Okay, so why? Why did we just break all of this down? Because honestly, understanding these 3 simple motions is the difference between a cool idea on a blueprint and a machine that actually works in the real world.
And this isn't just theory for a textbook, you know. The engineers who design the world we live in, they rely on this stuff every single day. As our source material puts it, this study is absolutely vital for designing the gears, cams, and basic mechanisms that run our world.
I mean, think about it. This knowledge is the key to everything. From designing the landing gear on an airplane, to analyzing the suspension on a Formula One car, to programming the incredibly precise movements of a robotic arm in a factory. Without this, we couldn't safely design a roller coaster, or create lifelike animations in movies, or even build the tiny, complex mechanisms inside your smartphone. This lets us predict, with incredible accuracy, how any system will behave before a single part is ever made. So, the next time you see a bicycle wheel spinning down the street, or a construction crane lifting a steel beam, or even just a simple can opener working in your kitchen, maybe you'll see it a little differently. You can now spot that hidden language of physics in action, the translation, the rotation, and that elegant combination of both that truly, really makes our world move.